So let's look at the what's happening with this ice skater of science. Okay, so initially our ice skater goes in, and he or she is just kind of skating along, you know, skating along. Velocity, mass, things that objects that have mass and velocity have what kind of physical qualities, quantities, physics type terms? Mass and velocity goes with kinetic energy and momentum. All right, so let's talk about kinetic energy. We'd have like 1/2 mv squared. Okay, and do you remember what momentum is? Momentum, isn't it mass times velocity? And truly it's a vector, so it has a direction. So then our ice skater goes into going along this straight line, and she then throws that leg out. So we've got an ice skater with a leg out here and throwing their arms out like this. Okay, so throwing those arms out changes what? What have we changed? Yeah, so we've got like an initial moment of inertia. The skater is still probably moving along to the right here. The skater still has a mass, but now the moment of inertia has changed. So we're talking like I of a cylinder plus I of, or 3 times the I of a rod, if you want to treat our arms like rods and our leg like a rod. Here, we've just pretty much got no big time rotation or no strange stuff happening, just a cylinder. So we're changing things up here. Then she goes into this spin business, goes spinning in here, and her leg is all bent like this, and her arms are all bent to her body like this, and she is spinning, spinning around with an angular speed, omega. So now what do we have quantity wise? Do we have kinetic energy 1/2 mv squared? Is she moving in the x direction anymore? No. Does she have a speed though? So does she have kinetic energy? What kind? Rotational kinetic energy. So we have some rotational kinetic energy, 1/2 I omega squared. So we get this ice skater spinning around, and we're not moving in the linear direction anymore. But she has mass, and she should have, and she's got a velocity. So what about the momentum? We had translational kinetic energy. Now we have rotational kinetic energy. We have linear momentum. Now we have, sure, and another name for rotational would be angular momentum. So the symbol for angular momentum is it kind of looks like an L, or have you, or do you remember in math the symbol for an angle kind of look like that? Like if it was an angle of 30 or something like that? Or it was angle, side, angle for geometry proofs and things like that. Anyway, so it looks like an L. You can write an L. I usually write kind of a swishy, running looking L there. Now, if momentum is mass times velocity, and we have these rotational analogies between linear quantities and rotational quantities, what do I mean? I mean, like, what is the rotational analogy for force? Torque. Very good. What's the rotational analogy of acceleration? Alpha, the angular acceleration. What about the rotational analogy of speed or velocity? Omega, angular speed. And then what about a rotational analogy for mass? Moment of inertia. Okay, so if momentum is mass times velocity, then angular momentum should be I omega. Very good. That's it. All right, so let's look at this. What was her initial angular speed? She was moving along a straight line on the ice. 0. What was her final angular speed? Not 0. Something. So she has some sort of angular speed. So if we go from having no angular speed to having an angular speed that's greater than the initial, so something that's not 0, what's happened to our kinetic energy? Is there a we've had a change in kinetic energy because we'll have 1/2 I omega squared minus 1/2 I omega initial squared. And change in kinetic energy is by definition work. Work is the net force times a distance. So in order to change this kinetic energy, we have to do work. And what did she do? How? How did she do work? Was anybody pushing on her? Her legs are out here. Her arms are out here. And what'd she do? She brought them in. Did she apply a force through a distance to move her body parts closer to the center again? That's a short leg there. So she's back as a tiny little. So we move the mass. Think about it. Well, let's put some dots here. So maybe the center of mass of her arms are here. Maybe the center of mass of her leg is here. And they're going to move through a distance. So she does work in bringing those quantities closer to the center, changing the moment of inertia. So she does the work to cause the speed to change, to cause the kinetic energy to change. Okay. So let's see. If our angular momentum is I omega, you know what? I remember this thing from linear momentum that like momentum is conserved, like P initial is equal to P final. Do you think that angular momentum was conserved for our skater that went from moving to the right at a V to moving in a circle?
Yeah.
Yeah, how could that be? How could we have the same amount of angular momentum at the beginning of her spin as she does at the end of her spin?
Because we're changing the moment of inertia.
Oh.
We're also changing omega.
So if the moment of inertia goes down, then the angular speed could go up.
Mm-hmm.
Okay. So this L symbol, angle symbol, is for angular momentum. Yeah. All right, so that's your angular momentum. This is our this is the moment of inertia. And this is the angular speed. Now let's talk about units. What's the unit for moment of inertia? How do we find moment of inertia? Okay, so mr squared.
So there you go.
Kilogram meter squared. You're multiplying mass times distance squared. What about angular speed? Omega radians per second. And remember, radian really isn't a unit, it's just a word. Makes you just feel good. Yeah, it can be per second, just fine. Whoops, sorry about that. And so our unit for angular momentum should be kilogram meter squared per second. Now, what if it is a point mass? Like, let's actually do an example. For example, we've got a point mass of 3 kilograms is moving, that's not moving, at 10 meters per second at a distance of 2 meters from the center of a circle. Circular path, there we go. What is the angular momentum? We have some ang moms. Okay, so if angular momentum is I omega, and if a point mass has a moment of inertia of what? Does anybody remember? So m r squared, and omega. I've got, what are you given up here in the question? What's this guy? Velocity, like linear velocity, because it's in meters per second. So how do I find the angular speed? How do we relate those two together? So omega would be v over r. Well, let's make a substitution then. That would be mr squared v over r. Oh, what would that simplify to? Oh my gosh, it's Mr. V. Cool, huh? So for a point mass, if you have its linear velocity, you can jump and find its angular momentum just like that. Pretty cool, huh? So let's substitute what we've got. Our mass is 3. The radius is 2 meters. And the speed is 10. So what do we get? 60 kilogram meters squared per second? Yep. Anybody else get that?